The most important thing, of course, is tenacity. How strong is it? Silk has a natural strength of about 3 grams per denier. Nylon, you can make it 3, 4, 5, 6. In fact, when nylon went into hosiery at first, it was 30 denier or 40 denier. The reason it was 30 denier, silk, natural silk is about 30 denier. So you had to duplicate the properties of hosiery and silk. So you engineer that make nylon the tenacity of silk. Now, when the first nylon came out, usually a pair of silk stockings would wear, first of all, only the wealthy could afford to wear or buy. And when nylon came out, the same denier, a pair of nylon you could wear it for a year. So, but then with silk hosiery, once you snag it, you get around and that was the end of it. About 3, 4 wearings. When you get your fingernail you could dig into it, that was the end of it. But nylon, that became a problem. In fact, so we started making nylon instead of 30 denier, 40 denier, 20 denier, 15 denier, because we had to get a life expectancy. Dr. Paul J. Flory came with DuPont in 1934. Dr. Flory was a physical chemist, and Dr. Flory was not interested in polymers at all. Dr. Carruthers got him interested, almost sold him the idea that polymers is a field that you ought to get into. Dr. Flory was a physical chemist and also a good mathematician. And Dr. Carruthers realized that the mind of Flory is needed in solving some of the problems in making nylon. Dr. Flory had a wonderful relationship with Dr. Carruthers. They were friends and also professionally respected each other. Now, one of the important things in nylon is the testing operation. How do you know whether the molecular weight is right? How do you know that all the physical properties are right? And I had a good luck or fortune to be asked by Dr. Flory to run some experiments for him. Electric metric titration for polymers. And it was more accurate, but very slow, because until you get you get a drift before the irons decide where to go. It took more time, more accurate, but it took longer to do it. That's where Dr. Flory came in. He had to develop a test to quickly determine whether the properties of the polymer is what you need. What do you need? Viscosity became very important. Molecular weight can be established by viscosity. You can do it by titration, relative viscosity, relative to another known viscosity, and that would also tell you the molecular weight by viscosity. But that was too slow. Intrinsic viscosity, relative viscosity, then he devised melt viscosity, that you melt the polymer on a certain condition, and the molten nylon is in a container on a controlled condition, and you drop a ball, and you time it. And that's called melt viscosity. Flory left only 4 years in 1938, and he went to teaching, I think, at Stanford. He went to several colleges. And that's where he became a specialist in the chemistry of polymers. People ask me quite often, what is nylon? How do you make it? And you start making nylon in a very simple way. You start with coal, air, and water. You combine it, you get a chemical called benzene. And from benzene, you start working it into the kind of chemicals you need to make nylon. Now, what you do from the coal, air, and water, you get it two products. One is called a base, a diamine, and you have to mix it with an acid. A base and an acid will give you a salt. That salt is called a nylon salt. The two ingredients combine to give you that product. That's the first beginning. That's the beginning of starting the process of making nylon. So what do you do with the salt? The salt is then put into a water solution and put into a test tube. That was the very beginning of making nylon. It was all made in the laboratory, in glassware, in the amount of about 5, 10, 15, 20 grams, which is about a half or a third of an ounce. When you finally get the nylon solution, you put the nylon solution in a test tube and place it in this glassware. You apply a vapor heat, and the temperature eventually combines the two chemicals. Diamine, it's called hexamethylene diamine, combines with acid, adipic acid, and after about 2-3 hours, the two chemicals combine and they form a polymer. Now it has to be cold drawn to get it into usable form. So you stretch it. Now it's finally stretched, but it still has 18% elongation. So when you use it, it'll give and come back, but it's stronger than steel. The first nylon came into a toothbrush. It wasn't necessary to make it so fine, make it bristle, make a filament. And the first was 1938. The nylon was made in the semi-works at the experimental station in Wilmington, and all the nylon made went into toothbrushes. That was Dr. West toothbrush. It went into paintbrushes. It went into fishing lines because the quality was not necessary in those end uses. It went into nylon rope, and that was nylon first used. Then we have learned to make it fine for hosiery, and that became a very, very important usage. The first market for nylon, the real market, was ladies' hosiery, lingerie. That was a very good end use. Here's why. It takes only about 1 ounce of nylon to make a pair of stockings. Any other product requires more nylon, less money, profit. So naturally it became very obvious that nylon would replace silk hosiery. And we had to imitate exactly how silk is woven into a hosiery. It's called full fashion. And the reason they call it full fashion hosiery, the nylon was woven in this open shape, and then the two ends were sewn together. It doesn't show it very well. And then you have a hose. And this became a very serious problem. So somebody discovered that if you take the hose and put the thing on this shape of a leg, called forming it, so the knit stocking was then pulled over this shape. This was heated, and the heat would set the molecules and stabilize them. Then no matter how much you washed it or boiled it, it would never lose its shape. So it's called pre-boarding. This was heated to a certain temperature to heat set it. Now, nylon molecules have a memory. Whatever temperature you get it out, the molecule will stay in that condition. And it will not change unless you raise the temperature above the original temperature.